Uranus is not only an absolute planetary maverick, but also a complete research mystery. No wonder, after all, the shimmering blue ice giant was only visited by Voyager 2 and studied up close, and accordingly, the data is sparse. Despite this, however, researchers have now succeeded in revealing a number of Uranus's characteristics that are as astonishing as they are confusing. The planet actually orbits the Sun on its side. Its magnetic field has not just 2 but 4 poles, and its surface is a frosty 216-degree ice, colder than it should actually be. But now, astronomers have finally managed to shed a little more light on the darkness of Uranus, and its strange 4-pole magnetic field probably stems from a remarkable spectacle hidden deep inside the celestial body. The Uranus family has grown because it was only a few months ago that experts announced they had detected a previously unknown moon in the realms of the distant ice giant. Accordingly, the number of Uranus's companions increased from 27 to 28. As befits a lunar baby, the newly discovered satellite is also the smallest of all Uranus's moons found to date. Christened with a provisional name S223U1, it's just 8 kilometers across. But the bigger question marks that have been swirling around Uranus for many decades are all the more reason to be curious. As already mentioned, this is primarily because the most up-to-date data available to us about this bizarre ice world still dates from 1986. But although the information collected by Voyager 2 may seem a bit outdated, it's still good for new surprises. In detail, the Voyager datasets revealed a strikingly strong radiation belt, full of energetic, fast-moving electrons in the planet's magnetosphere. The intensity of the particle currents was even comparable to that in the extreme magnetosphere of Jupiter. However, in contrast to the king of our planetary system, there was hardly any plasma in the realms of Uranus from which the electrons could have originated. This seemed all the more puzzling, given that the 5 largest Uranian moons should have been incessantly releasing water molecules into space, which would then be ionized by the magnetosphere of the ice moons. And so it was that for decades, experts struggled with the Voyager data. Only now have they managed to provide an explanation for these strange conditions. In fact, the key to the astronomical breakthrough was also hidden in the old datasets, but the scientists had simply overlooked it until now. This only changed when the team, led by Jamie Jinsky from NASA's Jet Propulsion Laboratory, took another look at the data. Voyager 2 had also analyzed the radiation and particle density in space in the days before and after its flyby of Uranus. But in fact, a strong solar storm had occurred shortly before the passage. This compressed the magnetic field of Uranus and tore the surrounding plasma out into space with it. While this event robbed the magnetosphere, the solar storm filled the planet's radiation belt with high-energy electrons in the same breath. If you like, Voyager 2 simply caught Uranus on the wrong foot, and by no means examined it in its normal state, but in an absolutely exceptional situation. Experts say that the planet's magnetosphere would have looked completely different if the probe had arrived just a few days earlier. Yet in a way, Voyager 2 did have amazing timing. After all, the extreme conditions at the time are likely to occur only about 4% of the time. Diamonds are raining inside Uranus. There is no question that the decoding of this almost 40-year-old plasma mystery marks an important intermediate step in Uranus research. But there is also no question that the ice giant's exotic magnetic field continues to present us with major problems. But how is a planet's magnetic field formed in the first place? Well, in the case of our earthly home, which is known to have a typical dipole magnetic field, this is created by convection currents in the liquid outer core, which act in combination with the solid iron core as a geodynamo. However, this so-called dipole field, which has 2 opposite poles, requires a certain minimum thickness of the convective layer. This does not appear to be the case with Uranus, and the experts' models show that a non-dipole magnetic field can be generated when the currents responsible are confined to a thin layer relatively far out. Furthermore, we know that the interior of the ice giant is composed of a solid core on the one hand and a mixture of water, ice, ammonia, and methane on the other, which is potentially conductive and therefore a candidate for a convective magnet, dynamo. What we don't know, however, is what the lower layers of Uranus look like, and what could block the currents at these planetary depths. One theory is based on the assumption that the water there assumes an exotic superionic state, which means nothing more than that the oxygen atoms of the water molecule form a solid lattice in which the hydrogen ions can move around freely. On the other hand, there is a theory that probably corresponds to the wildest dream of every jeweler. It could actually be raining diamonds inside Uranus. The fact that the interior of the ice giant may embody a planetary diamond is again due to the pressure and temperature, which are probably sufficient to break down hydrocarbons and compress the carbon into diamond crystals. In the same breath, this gemstone rain could also explain why the planet has a multipolar magnetic field. After all, the diamonds also tear gas and ice into the depths, which ultimately causes convection currents in the mantle. Since conductive molecules are also set in motion in the process, these would also contribute to the unusual Uranian magnetic field. So far, so plausible. And yet, a new series of research studies has now come to the conclusion that the magnetic field mystery actually has a completely different background. In this case, we are dealing neither with the effects of superionic water, nor with the consequences of the diamond rain, but with the result of non-mixable layers in the planet's interior. The solution to the magnetic field puzzle. The fact that the discussion about the magnetic field is now enriched by a third approach is thanks to Burkhard Militzer from the University of California in Berkeley. In detail, the doctor and born scientist used some high-resolution computer simulations that reconstructed the behavior of methane, water ice, and ammonia under the conditions inside Uranus. What was special about this was the fact that, thanks to an adaptive algorithm, Militzer was able to simulate the processes with atomic precision for the first time, with a surprising result. When the professor of Earth and planetary science looked at the model, the water had separated from the carbon and nitrogen. As a result, several layers were created that cannot mix with each other. At the very top is a conductive layer of water and ammonia, about 8,000 kilometers thick, which is probably partly liquid. This is also the area where the convective currents take place, which act as the engine of the multipolar magnetic field. Just below that, there is a similarly thick zone of nitrogen-containing hydrocarbons, whose hydrogen content decreases with increasing depth and pressure, ultimately resulting in several layers of these compounds that become steadily denser. According to Militzer, this circumstance prevents vertical flow, which is why these layers cannot play a significant role in the formation of Uranus's magnetic field. In other words, the hidden interior of the planet behaves like oil and water, and the bottom line is that the division into two emiss layers can explain why Uranus has such an exotic magnetic field. But as is so often the case, the theory still needs to be put to the test in the course of future investigations. This could be done, for example, in the context of laboratory experiments under high pressure, or in the best case, of course, in the course of a direct on-site exploration. The sobering future of the Uranus missions. Unfortunately, the truth about space probes is that there is currently simply no program that has reached an advanced stage of development and would go beyond the status of a vague concept. One of these concepts goes by the name Anus and includes two individual probes, one of which flies to Uranus and the other to Neptune. If the project conceived by the ESA is actually realized, the separable probe could make its way into the gigantic expanses of space in just under 10 years. Whether and when this project will actually be realized, however, is currently still written in the stars, and with it, all the answers to the Uranus questions that are still unanswered. As briefly mentioned at the beginning, the ice giant is tilted at almost 90 degrees, and its rotational axis is thus in stark contrast to those of all the other planets in the solar system. In principle, researchers assume that the celestial body was tipped on its side by a massive impact. But exactly how this brutal event unfolded and how it influenced Uranus in the period that followed is still an unsolved mystery. A simulation had shown that the ice giant could have collided with a protoplanet twice the size of Earth about 4 billion years ago, and since the oversized collision partner hurled ice and rock into the core of Uranus, this incident is sometimes used to explain the planet's multipolar magnetic field. However, this also applies to the inexplicable coldness of the celestial body. Although Uranus is not the outermost planet of the solar system, it is the coldest of all, with a minimum temperature of 224 °C. In this regard, the collision could have stored enormous amounts of ice in the outer reaches of Uranus's mantle, significantly affecting the planet's heat flow. The collision of your click with the subscribe button can store our videos on your YouTube homepage. Become a part of our community now to never miss a new post from us again. We'll see you soon.